Welcome back. We continue where we left off for chapter section 8.1, equations of lines in 2 space and 3 space. So we left off on question 11. Question 11 asks us, given each scalar equation, write a vector equation and the parametric equations. Okay, so I realized when I did this problem, I might have done it quite a long way than someone might have. So but I prefer my method actually. I really like as an intermediary step using the slope-intercept form because I think it spits out the vector equation quite easily. So what I did is from the scalar equation of a line, which we're given, I found the slope-intercept form. That's just by isolating for y. So that's what I did right here. Okay, perfect. But then the problem is really simple, right? Because the vector equation asks us to find a direction vector, which we have from our slope right here, m. And it asks us for a known point on the line, which we also have as the y-intercept. So we have both ingredients for to write the vector equation of a line. So 0, 3, this is the y-intercept. Our slope gets transformed into a direction vector, so 2, -1 right here. And we're golden. Because now we can just write our parametric equations, x equals 2t and y equals 3 minus t. Perfect. Same ordeal for 11c. I took my scalar equation right here, transformed it into its slope-intercept form by isolating for y. Okay. Then the vector equation is spit out really nicely. You just take your y-intercept as the known point on the line, so 0, -13/2, plus t, our slope gets turned into a direction vector, so that its corresponding direction vector would be 2, 5, rise over run. And now it becomes run, rise, and components. Okay, and then the parametric equations are also spit out quite easily after that. It's just x equals 2t, and y equals -13/2 plus 5t. Beautiful. Oh, I should also mention, I guess, I didn't mention in the last video, but a lot of solutions for this chapter are might be quite different to what you get. That doesn't mean your solution's wrong. It just means that you came across it a different way. So don't be afraid of that. If you find that you're unsure about your solution's validity, you can always come ask me in person. I can help you verify it. Okay, continue on. So we have question 12. Given the points A, 3, 4, -5, and B, 9, -2, 7, write a vector equation and the parametric equations of the line through AB. Okay, so remember, for a vector equation, we need a direction vector and a point. A way to find a direction vector is if we have 2 points, we can find the vector between them, and that corresponds to the direction vector. Okay, but we also need a known point. That's easy. We can just use one of the points that we're given. Okay, so that's exactly what I'm going to do. So, for question 12, I just find the vector between them. I treat that as my direction vector, so AB is M as well. So the vector between AB is 6, -6, 12. That's goes here then for a direction vector. For here for a direction vector. And then the known point I use is A, but you could have easily have just used B as well. No difference. And then again, your solution will probably be different if you use B, but to find your parametric equations is the same step as before. You just take your x's plus t times 6. The y is going to be 4 minus 6t, and z minus 5 plus 12t. Okay, good. Question 13 asks which points are on the line. So I only solved, I solved all of them. I solved A, B, C, and D. Okay, so let's go over all of them then. So again, similar to the last problem, I didn't even start my problem before I at least wrote down my parametric equations. That's how you do all these problems involving whether this point's on the line, or we'll later on see if this point's on the plane. So my parametric equations, I have 1 plus 2t, y is equal to 3 minus t, and z is equal to minus 7 plus 3t. Always remember, though, to put x, y, z, x, y, z. That's what it's equal to. Okay, I found my parametrics. And then I just shove in any point I have into those x, y, z's. Okay, and similar to the previous video, I solve for t in each one, and I see if it gives me the same value. If it does, the point lies in the line. If it doesn't, the point doesn't lie in the line. For part A, all t values are the same. They're 3. It's on the line. The next guy, same thing. I just plug in 2, 1, negative 3 into my parametrics. I get different t values, therefore it's not on the line. Even once you recognize that 2 t values are not the same, you can immediately say it's not on the line. Part C, same deal. Plug in my points, points components into the parametrics. Solve for t. I get the same t value. So that means this is on the line. And finally, for part D, I check to see if the t values are the same. And in this case, only the y parametrics, I get 5 over 2 instead of negative 5 over 2. So this differs from its two companions for y, x and z, meaning it's not on the line. The difference was a negative. Okay, perfect. So that's question 13. Moving on to questions 14 and 15. So in each case, determine if L1 and L2 are parallel, perpendicular, or neither. So this problem is quite simple. What I did first is I transformed each line into its vector equation form, and then I examined the direction vectors. So if a line was not in its vector equation form, I did that first before I even proceeded. So this line in scalar equation form, I first turned it into its slope-intercept form, or y equals mx plus b. Isolate for y. Okay. And then I use my known point on the line as my y-intercept, so 0, negative 3 over 2. Plus, my direction vector is the slope of the line, so that's 3, 2. Okay. But line 2 in this case is already in vector equation form, so I don't have to fiddle with it. Now I just look. Now I look at M1, which is here, and I look at M2, which is here. So are they scalar multiples of each other, or is their dot product 0? That's what I'm asking myself. In this case, they're scalar multiples of each other because just 1 times M1 equals M2. So therefore, this is a neat symbol for meaning parallel. I don't know if you've seen it before. So line 1 is parallel to line 2. Done. Part B, same deal. I have a equation in scalar or standard form. Transform it into its slope-intercept y equals mx plus b form by isolating for y. Then its vector equation, I use the y-intercept as the known point on the line, and the slope becomes the direction vector, so it's 9, negative 1. Perfect. Line 2 is in parametric form this time, so that's a quick transition. So there's no, for x, there's no number in front, meaning it's going to be 0 as the x component of the position vector. There's a 15 out here, so that's going to be the y component of the position vector. There's a component of 1 in front of the t of x, and there's a component of 9 in front of the t of y, so it's 1, 9. And now I can examine the direction vectors, M1 and M2. I'm looking at this. They don't look like scalar multiples, obviously, so I'm going to attempt the dot product just to see. When I attempt the dot product, M1 dot M2 of the direction vectors, I get 0. That can only be the case if the lines are perpendicular. So, and that's what I stated right here, line 1 is perpendicular to line 2. Okay, good. Problem 15. describe the line defined by each equation. Can't really get a handle for this problem unless you graph it. So that's what I did. Okay, so the first one. This is quite simple, right? So I can actually graph this even without putting into slope-intercept form, and I'll show you how. I'm taking, this is the known point on the line from the vector equation, -2, 3, right here. This vector you should recognize from our last unit. This is I. So I just means I'm traveling horizontally in both directions. If I'm scaling it by this parameter t, if t is negative, I'm going to the left. If t is positive, I'm going to the right. So that's what it looks like. It's just a horizontal line. Okay? That's why this problem was quite simple. B. So B was the line T001. So 001 is also a vector you should recognize. This is K in 3 space. So that's just a vertical line that's along the z-axis, exactly along the z-axis, actually. So yeah, vertical line in 3D along z-axis. Okay, good. C, same deal. This is the vector 1, so the point 1, 1, the known point on the line, so it's like right here. I should represent that like this. Okay. But then S05, the way I see it, is just 5 times j, right? So it's just a bit longer than j, the 0, 1 vector, but it's still going to go up and down. So it's just going to be a vertical line, right? If s is negative, I'm going down this way. But if s is positive, I'm going up this way, right? This is actually quite a... there's a concept in first-year linear algebra, which you learn called span, which makes understanding this problem quite simple, but I think I give a pretty decent explanation, hopefully. Okay, part D. So we had the line xyz -132 plus s101. All right. So this is a bit hard to graph for me. But, so this is the known point on the line. -132. That's what I graphed right here. Boom. Okay. Now 1, 0, 1. This is a vector. So this is a line, actually, that its y-coordinate is actually frozen at 3. Its y-coordinate is frozen at 3, and it's, you can imagine it coming at you. So the line is actually, you can imagine literally poking you in the eye from, if you're watching this on a screen. It's literally coming at you because you can think of this vector as a vector I plus k. Okay. So this vector is literally coming at you. The note I wrote here, let's see the note I wrote here. The y-coordinate for this line is frozen. Imagine it coming out of the page. Oh, so it's just what I said. Yeah. I think it would be best for everyone to graph this in GeoGebra for you to see it if you can't understand what I'm saying. It's quite a good exercise, I feel like, for using GeoGebra as well. All right, I think we'll pick up from question 16 in the next video. I'll see you then.